Mr. Aditya, a senior research scholar in the department pursuing his PhD with Professor Ravi Gudi. I request Aditya to continue the session.
Thank you, Krishna and Nilagri, for the warm welcome. I once again welcome all of our esteemed panelists that have with us here today. As my friend have briefly introduced, we all are greatly affected by MIAL in our daily life. This makes today's topic of discussion, intersection of chemical engineering with AI/ML in Industry 4.0, very pertinent. This topic is already influencing businesses and it has more to offer. So we are honored to create this panel who will share their knowledge and experience and answer our burning questions. So without taking much of your time, let me ask panelists to give their brief idea on this topic. Please.
Yeah. Good afternoon, everyone. So I thank the Research Scholar Symposium team to invite me to participate in this event. So it's so I would like to keep the things simple as much as possible from my side. How this technology, the AI, ML, or the digitalization from the broader perspective, how it is useful in the industry, how it is getting implemented, and what are its potential benefits in the chemical industries, what will be the future of this, so where this technology will take us. So that journey of digitalization, it started with Industry 1.0, then Industry 2.0, 3.0. So earlier we were not having any, it started with the programmable logical controllers, and then came the DCS. The operators were using the DCS to control the plant. So earlier, the operator, the field people, they used to go to the field, they used to change the wall, operate the plant manually. And then came the DCS where the operators used to like sit in the DCS control room, and from there itself they can change the set points in the process. They don't have to go to the field, change some set points in the change anything in the field. So from the control room itself, they are in a position to run the plant in a very efficient way. And then came like the capturing the data, like the era of digitization. So whatever the data, whatever the trends, the numerical values which we are seeing into the DCS. So how that data is to be captured into the into some form wherein like we can use that data and get the meaningful insight into the process for the improvement. So with that, like the digitization of the process variables, like whatever we have the measurements like temperatures, pressures, flow rates. So those are like those are stored into the historian. That is like the hard drive, we can say, where this data is getting transferred from DCS control room through the OPC server into the historian. So now to like that data is getting stored into the historian. So what is the means of like analyzing that data? So what needs to be done with that data and how is to be done with that data? So the software is required to analyze that data. So the various softwares are available in the industry like Aspen IP21. So whatever the data we are storing in the historian, so it is the operators or the technical people or the R&D people, they can see the data in Aspen IP21. We can see the trends, we can do the calculations, we can do whatever is required out of that. So, so now like the digitalization, this data is available, enormous data is available. How this data is to be utilized to get the meaningful insight. So some of the data you can develop the insights, meaningful insights to get the better decisions by the operator. If the quality data or some critical parameters which are not available, or the quality data is like they measure in the lab at 4 hours interval or 8 hours interval. So now whatever the data is available in the lab, so the operators are taking action based on that 8 hours interval information. So whatever the action the operators are taking, it is not in a real time, and the action which they are taking by the time the operator takes the control action, so the significant amount of time is getting elapsed, and there is a considerable variations in the process. So it is not a real time. So whatever the process variables we have, which is impacting the quality, yield, productivity. So how that data can be leveraged to develop these sensors for the quality parameters predictions or the desired parameters. So that kind of the AI and ML methodology or the technology which we are leveraging today to develop the sensors, the predictive models, which can give us the real-time information, right? And it is enabling the DCS operators to take corrective action in a real time, so that whatever we should get the first pass quality. We should not generate some waste product or off-spec generation, something like that. So, so we like at ABSTC, we are a corporate research and development center for the Aditya Birla Group. So we have various businesses like carbon black, aluminium, fiber. So in all these businesses, we are developing the data-driven models, the soft sensors for predictive models for the parameters which are measured very rarely or at less frequency. Apart from this data-driven modeling, so whatever like the data-driven model we are doing, so it has to be have the solid foundation of the process understanding. So without the domain knowledge of that particular process, whatever the data-driven model which we are developing, so those are not robust enough. So take for instance, if I am developing the soft sensors for the carbon black plant, and only based on the data, so I know, okay, these are the process variables, and I don't have the process knowledge. I have never gone to the plant. I have never discussed with the DCS operators or the technical people. I don't have the process understanding. Then whatever the soft sensor I am developing, so it not be that accurate. So our methodology is like we regularly visit to the plant, we sit with the DCS operators, we gain the process knowledge, we understand how they operate the plant, what is their operational philosophy. So each and everything, because the operator, if I see the operator is operating that reactor for last 50-20 years. So we as an academic PhD person, for example, if I am a PhD academically, so I may not understand what is the reactor, how that reactor is operating. So the person who is operating the reactor since last 15 years, so he is much more than the doctorate. So I need to sit with the operator, understand the complete physics of how he is operating, what is the science behind that, and then understanding the complete process and incorporating that knowledge, understanding into my model. Then it becomes a robust model which is ready now to be deployed into the plant. So this is a methodology which we use in almost all our businesses. So all our scientists, corporate R&D scientists, we regularly visits to the plant. We have very close interactions with the DCS people, get very in-depth understanding of the process, and then based on that, whatever the methodologies we have, AI, ML driven models, we also develop the physics driven models. So since the topic is Industry 4.0 digitalization, so in that various the modeling methodologies are incorporated, like physics driven modeling. So like we develop the heat balance, mass balance models in various simulation softwares like Aspen Plus. So it incorporates the process, the dynamics of the process, the process understanding, the thermodynamics. Then like whatever so these models will provide us with the predictions which are the measurements which are available in the plant. So those are we utilize to validate our models. But if the measurements are not available in the plant, for example, if my gas composition is not available, and that is not possible to measure frequently in the plant. So my the physics-driven model provides me with the gas compositions, temperatures, flow rates. So that becomes another methodology which is a physics-driven model. The another thing which we use is like the CFD modeling, computational fluid dynamics, wherein to understand what is happening inside that equipment in a detail, how we can improve the process or the efficiency of that equipment, or if it is facing with some challenges, how we can overcome those challenges. So those methods is also we use mostly in our plants. We develop CFD models, we validate those models with the plant data, and then we discuss with the plant team and implement those solutions in the plant. Based on whatever the results we are getting, so we discuss and make the modifications in the plant. So these are all so this is, so let me, so whatever the journey we are seeing at this point of time, the Industry 4.0 digitalization. So I have seen the days where we didn't have this data, whatever we are seeing at this point of time in Aspen IP21 or some other platforms. So wherein we get all the data, process variables data, the lab quality data in a single platform. But I started my career, I remember those days where we didn't have this data, live data. We could not, there was no platform as such wherein we could see the live data in a single platform. So I used to sit with the instrumentation engineer, and the storage capacity was just 45 days. So he used to, instrumentation engineer, he used to give me the data for 45 days for the process parameters. And then I used to go to the laboratory from where the logbooks were there, and I used to note down those lab quality data in my notebook or enter into Excel. And then I used to do the timestamp matching of that process data with the quality data. And then I used to develop these models, and again then used to implement in the DCS. So I have seen those days also, primitive days where we didn't have data and we used to struggle to get the data from the plants and develop the models. So now we have seen that journey. So we are at this stage where we have everything like process data, quality data, whatever is required. We have that everything in a single platform. So also the data analytics techniques have been developed over the period of time. So right now at this since last before 3 years back, one of our business, Birla Carbon, they have implemented a platform which is known as SEEK. It's an American company, and we have 16 manufacturing units in India as well as outside India. So it's a platform wherein we have connected all these 16 manufacturing units, the process data, the lab quality data, everything. So now I can see the data of all the 16 manufacturing units in my laptop. I can pull the data, whatever is required. I can do the pre-processing of data. I can develop the soft sensors. I can push into the system. I can give it to the operators. They can see the predictions and they can take action as per their requirement. Also, the other platforms are there in which we have this Python programming wherein we can write the code to generate the predictions, and then we can write the control systems also. So this is what the journey of digitalization which we have seen in our corporate R&D ABSTC, and it is really this digitalization journey has picked up the momentum over the period of time, and it will have a good future in chemical industries moving ahead. Yeah, thank you very much.
So that was a very comprehensive answer. First of all, so again, it's a pleasure to be back in IIT Bombay. I was here recently, I think about 5-6 months ago, giving a seminar on kind of a related topic, which is explainable AI. It's a pleasure to be back here again talking on the same topic. Perhaps what I mentioned there did not reach the right audience, so I'll try to do it again. But to go back to what was mentioned previously, AI, ML in the chemical industry is both very new and very, very old. Right? What do you mean by very new and very, very old? Very, very old because if you look back in the history of using data for making decisions, which have a very high value add in the chemical industry, particularly oil and gas, it's been happening since the 1960s. If you look at the history of computing, the 1960s there were no PCs, there were big giant mainframes. Those mainframes bought for millions of dollars were being used by companies that we know by the name of Chevron or Standard Oil, Exxon today for making decisions on how to set up, how to calculate the set point for a FCC unit, a fluid gas tracking unit. This is back in 1960s, okay? We are now here 60 years later. Everything you described, in a nutshell, reduces to that. Eventually, your plant runs because somebody has decided what should be the set point. So in that sense, the structure has not changed, and that's why I say that really nothing has changed. But obviously, everything has changed because only the Exxons could do it. You had to be an equivalent of $1 billion company to be able to do that back then. And today, a mom and pop shop, a small plant, can afford the same technology to deploy, to do quality control in the facility. You don't need very expensive hardware, software, or peopleware to be able to do AI, ML in the plant. At least that's the way I see it. But AI, ML, at least in the chemical industry, does not stop only in operating the plant. If you look at the life cycle of the plant, right from inventing the chemistry, which is going to give you the products, to scaling it up to kilo scale, designing the process engineering of it, to operating, to designing and running your supply chain, whom they procure raw materials from, whom they sell my products to. every one of those steps, AML plays a role. So the decision makers are plenty, right? On the first stage, when you're doing discovery, we're talking about chemists who are saying, what are the things I should be looking at to get better conversion? How do I design my reactions better? So to give you a very practical example, that's a project that we are currently working with a big multinational company. They have 200 chemists sitting in their labs here in India. I won't tell you their location, who are discovering new chemistry. Okay, they already have a bunch of tools to help them figure out, is this promising route that they should invest their effort on, or let's put this particular branch aside, let's focus on something else. The project that I am talking about is not about the chemistry, it's about the chemists. The management is very concerned that the chemists don't wear their PPE, their lab coat, their goggles, safety goggles, the gloves, when they are doing hazardous stuff. So where is AI/ML used? To monitor the chemists. So the cameras which are in the labs would give an alarm if this chemist takes out his safety goggles and forgets to put it on before he goes meddles with the chemistry. Okay? So that's AI/ML, because you're taking image data and then figuring out whether this guy is wearing the right PPE for that particular task, experiment, and then gives a report that this guy in the last 1 month, there are 4 instances when he operated his experiment without, right there. Process engineering, where you are now building a plant, you have to develop flow sheets. Historically or traditionally, it's done by using our chemical engineering knowledge, right? But if you look at how we write documents today, or maybe how you form a text or a WhatsApp message, you type first word, WhatsApp will automatically tell you these are the next 3 most likely words you're going to type. Apply the same thing to flow sheets. You pull in a reactor based on historical data of similar flow sheets. It can suggest you that these are the next other downstream equipment that you want to probably add to your flow sheet. Okay? And so putting together the flow sheet becomes less error prone. Not that the AI is going to give you a brand new flow sheet which is totally novel, but what it's going to do is make sure that you don't, by mistake, overlook a pressure safety valve or the right sensor or what have you. Still on the topic of safety, you probably have to do a hazard and operability analysis multiple times, perhaps during the life cycle of the design. Lots of time and effort goes into doing a hazard. Much of the work, I would say 70 to 80% of it is routine, and 10 to 20 or 20 to 30% of it is something that's very specific to that flow sheet, that particular layout, that particular facility that's going to come up or has come up. So why not automate that 70% which is very common? That's now, there are tools, as-of tools, which will tell you as you say that I'm talking about this particular equipment, let's say a reactor, knowing what is the chemistry happening in the background will tell you that you need to be worried about overflow, level control, what are the safeguards in there. It will automatically pull it up, and then the HAZOP team leader has then only make sure that the team contributes to the things which are not already captured by the machine learning. Operations, I will not comment on that much more because it's already been said. There's a lot of use of decision support tools that the operators are now using regularly. When I use the word AI/ML, I would say that even advanced control techniques that we do not associate with AI, for example, model-based control, MPC, again, that's chemical engineering for the last 40 years. Almost every refinery in the world has MPC today. It has the same challenges that AI/ML has in terms of the operator sitting in the control room, the board operator, has very little insight into the optimization which is running in the background and generating the set points which are the output of the MPC. So the inscrutability of the MPC is the same issue that pops up when you deploy a neural network to do maybe a quality prediction. Okay. So the solutions that are required are essentially the same. So that's on the operation side. And then similarly for supply chain, most chemical products get bought by other businesses, not necessarily by consumer. Which means you are talking about keeping track of where is my fleet carrying all my products in this map. Can I track them through GPS? If a truck is delayed, can I have advance warning so that if I have inventory down, inventory up situation, I can do some proactive actions. So like that, so I believe that AI/ML has made fairly significant change, but the building blocks have been there for a long time. The building blocks being data. The chemical industry has had access to large amount of data, particularly in the operation space for the last 60 years. So that's made it easier to deploy.
Sharad, sir.
So I will take an even more primitive view that if you see chemical engineering, it has gone through more than a century of evolution. And during this evolution, it has gone through many phases. So for example, I'm sure when numerical methods started making an entry to chemical engineering, people might have had a similar discussion, chemical engineering and numerical methods or transport phenomena, because things started to get quantified. Okay? And but essentially, what was numerical methods? Of course, numerical methods was a way of solving your transport equations. But transport phenomena was a way of systematizing knowledge. So whatever knowledge you had, which you had built up in terms of heuristics, could be now put in terms of an equation. So if you have 100 data points, now you have one equation which can explain those 100 data points. So it was in some sense compression of our understanding that we could do through transport phenomena. So this is the same journey that continues from transport phenomena to subsequent manifestations, whether that manifestation was in form of AI, which was very prevalent, or one of those manifestations is ML, which is now become very popular. But that underlying idea, or the underlying strive to be able to systematize knowledge and be able to learn and hold it all together is also evident over here. So now coming to more specific points. So chemical engineering has been dealing with this for quite some time. And in terms of AI, so process control has been in this domain, the operations and controls as we call it, has been in this domain since, as Raj mentioned, since 1960s. So they have been dealing with it. Things have changed along the way. So conceptually, many things, including MPC, were there right from 1960s. But what we did not have was an opportunity to be able to solve things in real time. So these things have kept on changing, and the concepts have become numerically more refined. So like you had expert systems. I know that Raj and your supervisor used to be in 1980s, 90s. They were one of the most well-known teams in terms of expert systems. Then you had neural networks, and neural networks evolved, and now you have pipelines of neural networks. If you're doing image recognition, it's not just one machine, it's now a pipeline. You have multiple machines which come together. So these are manifestations that have really become possible, and as you have also mentioned that earlier we did not have that kind of ability to see everything on the screen in real time. So there's a lot of hardware and computing that has allowed those original concepts to be refined and become more and more useful. So, but I always remember that journey that eventually from some set of heuristics you went to understanding of a mechanism, you put it in terms of an equation, you were able to build a simulator, and now the same thing we are doing with data. So you have huge amounts of data. Instead of just plotting X versus Y, can you do something more in terms of getting a machine to be able to represent all the data? And we've got better at it because of availability of hardware, and people have become more open to it. So NLSO used to be very popular even in 1960s when there were a lot of people who had started, And they said the same thing, that this is a revolution. But it, after 1970s to 80s, it went dead. Then again it came up in 90s when the backpropagation algorithm was proposed in 1986. So again there was a huge amount of interest in NLs, but again it hit a roadblock. So it's an idea which comes up, it gets tested by reality, and then maybe it gets modified into something new. It's that same human scientific journey is how I look at it.
Thank you, sir. So, coming to my question, so as we say that in MINL, data plays very important role, and we are using it to control, and safety is a very prominent thing in a chemical plant. So, how close are we to completely remove the human interfere in controlling the operations? And is AIML is able to predict the unsafe operations or predict the trends? How close we are to achieving that?
So answer to this question is like the control system which we build based on the data-driven model. So it is based on the process variables which is having operating region. So there are like the operating limits, the design limits of that particular equipment. So considering the design limits, operating limits, so whatever the substances or predictive model we are developing, so it is within that range. So we have a wide range of data for those particular process variables. For example, like we will have for some plants 5 years or 6 years of data set. So we use that data to develop those sensors, and then based on that, like we develop a control algorithm to implement into the DCS. So it is like a kind of step-by-step procedure. Once we start implementing in the DCS, so we have to ensure that whatever the data we are feeding into the predictive model, it should be within the limits, and the prediction should be within the limits, so within the safety limits. So it should not do anything which is hamper to the quality, or it will cause the plant to get shut down, something like that. And then based on that, like the alarm system is generated into the system if that particular parameter, if you are taking that control system into the auto mode or cascade mode, so it will, and if I feel, if the operator feels, okay, now, so it is going outside the limits, so then it will automatically generate the alarm. So immediately the operator takes that system into the manual mode. So all those safety considerations are those are considered, so that there is a minimum risk. So once these control systems are tested, then so it is a step-by-step process to take the trials, get the confidence on the control system, and then we can run for a longer period of time. So that way we ensure the safety of the plant. Yeah.
So your question was, given that there is so much data, can we build models which can predict if the plant is going to be operating in a safe fashion or not? So let's take
without human intervention, how close?
So let's take an analogy, right? So IIT Bombay probably has out of 10,000 students, and let's assume that students show up for 100 days a year. So I have 1 million data points of students attending classes. So I have, from these 1 million data points, can I predict things about people's health, students' health? Pretty soon you will realize that that question doesn't really make sense, right? Because students probably show up for class only if they are well. If they are unwell, especially if they are seriously unwell, they probably will not be in your data set. The same thing happens with plant. So if my pump starts breaking down, but still it's functional, I have data for it. But if it's broken down, then I would not be using the pump, and my historian will not have those kinds of failure data. Since data is not there, any model that I build with the data is going to say a lot of things about normal operations or close enough to normal operations, but it will not tell me much about how the pump breaks down, when it breaks down, all that stuff. So you need to have an understanding of what is the nature of the data, what's the richness of it, and then be able to utilize it for that purpose. So if, on the other hand, you go to a pump manufacturer, and the pump manufacturer is very concerned about the entire life cycle, but only of their pump, not of how it interacts with the reactor and the column and the heat exchanger and so on. So they would generate data about the initial break-in period, the normal operations, but also of the failure. So the pump manufacturer can give you a model or can develop a model which can tell you things about the health of the pump, but it's very difficult for the operator who is just buying a pump off the shelf, assembling it into a plant, for them to have data about its non-normal operation.
So I'll also add to this. So as you understand, whatever we build using data, and what Raj referred to was the fact that your data set is imbalanced. You have more normal instances than abnormal instances. And now you're trying to build a model, so you can ascribe some metrics. You can say that the accuracy is, and that is what we do whenever we build a model. We try to ascribe some metrics to the accuracy of that model. Now, as Dr. Mankar said that they are also monitoring. So there is a watchdog on top of that model, which is trying to say how good this model is. And being in the industry, you can't afford to have an accident. So you have to play it safe. So just like you have a type 1 error, type 2 error, so you can try to tune your watchdog in such a way that you can afford when you give a false alarm, but you don't want to have a case where there is really something is going to go wrong and you are unaware of it. So you can tune, you have something to play with. But the problem with data-driven models tends to be that they don't fail gracefully. So if I have a linear model of the system, or if I have a transport model of the system, and I see that it is becoming inaccurate, it probably will, instead of the viscosity being some, it might give you a 20% poorer prediction. Okay. But it can happen in a database model that if your height is, it might just say the height is -5 centimeters, which makes no sense. Okay. So the failure mode of a data-driven model can be, it may not be very good. So we need some kind of a watchdog which makes sure that you don't enter those zones and you have enough probability of success of making a good prediction. So those safeguards are probably more important with database models than with others. And running a plant fully autonomously, I think we've heard last year that there was some plant run by a Japanese company in Bangalore. There was a news item which ran for 1 month completely autonomously. And there seems to be interest in the industry to run a plant autonomously, just like a driverless vehicle. So again, like a driverless vehicle, you have to put those safeguards in, because something fails, the failure can be catastrophic. So with that caution.
Thank you, sir. I have a long list of questions, but in the favor of time, let me open floor for the question answers, if anyone have any questions. Abhilash?
Hello, sir. My question is to all three panel members that how do you see the future of research startup related to AI, ML and chemical engineering?
So, see, there's probably, like everything else, there's probably a lot of hype also associated. So a lot of companies, because you feel that you don't want to miss the boat. So there are a lot of people who are trying to invest efforts there. Some yield fruit, some do not. And I think that it is this speculative phase which is there right now, because there are so many things that you can do. So if I come to something very simple, if you have, let's say, an MSME company which has a batch reactor, and they have a display of temperature, which is not, but they don't have a DCS system or any data acquisition. So you could simply put a camera where you could read off what a number is, do a character recognition, and put it in your Excel file. So with a very low cost. So I think these low cost solutions in chemical engineering will definitely. So finally, it's all economic value. If they're able to give economic value, then that startup will be successful. Yeah.
So I'll probably give a positive spin to what this said, Sharad. So it seems to me that if you look at companies, both large and small, they have the same fear of missing out. Every CEO, every C-level person has heard of AI/ML as something that is making a big dent to business, and they want to be seen. They want to be doing something in it. At least they want to be seen to be doing something in it, especially if they are listed in the market. So now some of these things, there are large number of low-hanging fruits which you can go to a generic company. Let's say you can go to Microsoft. You can get a chatbot which will help clarify if a person is eligible for leave or not. This is the first generation of AI/ML that even chemical industries have got themselves into, where they go, have regular kind of business-oriented AI/ML tools deployed. Right? The second generation is where you're now saying operational matters of the nature that we have been discussing here really pop up. Companies have come to realize that either they need to have fairly extensive expertise in-house, or they have to outsource it to outside players. Right? The outside players are not necessarily only the Honeywells, Yokogawa, ABB. This is the space where I have seen number of instances where startups from IITs and other places have managed to win contracts, small contracts, let's say 3 months, 6 months kind of contracts, to develop something from that plant's data and help deploy it. The outcome has been a mixed bag by all measures. I don't think I would say that every one of those ventures have succeeded, but startups are being accepted as a low-cost way to explore if AI/ML can deliver something of value to even big companies. So I would say that I'm at least cautiously optimistic.
Sir, I have a question. Am I audible?
Yeah.
So, you might know that earlier when no computers were there, people used to interact with by the name. They used to do everything. Then the phase came where small cards like with name. Now they have been VCF, like in automatically everything gets saved in the phone. Now my question is, what should be the starting point where AI/ML, because you said, as sir said, that if a pump breaks down, it gets damaged, then in that case, all the data that has been generated gets wasted. So there's no use. No new pump, new data will come. So in that case, should the AI/ML, the data creation should be with respect to first pump manufacturer also, and if pump manufacturer goes, then in that case, like it's a series from where something starts. So what should be not focusing on the only industry, but the whole back series which makes that industry work? Do you think that that is also important?
Yeah, so let's go back to the same example, right? The pump manufacturer wants to sell not only a pump, but he also wants to sell a bunch of services. That way, he increases his revenue share, right? So the pump manufacturers are developing AI/ML based tools to give you a health indicator on the pump or on the valve or any such common piece of equipment. And because they have access to hundreds of pumps of the same make,
that data is a lot more homogeneous, and therefore the models that come out of that data is quite accurate. And they also know what has gone into the design of the pump, which a buyer may not have access to because it's a black box as far as the buyer is concerned. And so they can even develop physics-informed neural networks or other hybrid models, right? So it's an advantage for the pump manufacturer to develop models which give me insight on the health of the pump. As a chemical plant operator, I want to be able to take the results that's coming out of the pump, bury it into my own DCS or other systems. So rather than taking data and do the analytics all over again, I should just take the result that this pump is throwing out and be able to merge it with the others, the results from the other systems, and have a fully cooked product or outcome displayed to my operator. So the operator knows that pump is breaking down not because Aditya Birla's neural network came up with the answer, it's because Kirloska's pump threw out that answer.
Do you have a take on it?
So to add to sir, is that like pumps, the air blowers, whatever the equipments, rotating equipments are there in the plant. So those the data will be comprising of the normal operations data, as well as the failure data, as sir has said. So sometimes before it fails, so it will have that specific failure data. So the predictive maintenance of equipment of interest. So it requires that failure data, because using that data, the industries are developing the model to understand what will be its remaining useful life. So that failure data, it helps to predict in advance. Okay, after 30 days or 45 days, this pump or blower is going to fail. So it allows the plant to understand the dynamics and schedule the maintenance. So it gives you the asset reliability, predictive maintenance of equipment beforehand. So if you are developing those models in offline platforms, so there you are incorporating the perturbations into the model, disturbances, to do that failure analysis, and then based on that data, these models are developed. But in industry like plants, we have that failure data, so that is also very much useful, which helps to understand the rotating equipments. So I hope I could add.
Yes, sir. So there's one more follow-up question to it. Do you think that standardization of these models that every industry can use, for example, you have seen these valves, these nut bolts, all have some standard measurements, apart from the self-make ones. So these standard ones are able to help not only one industry but everyone. Anyone who wants to build something in their household, or anyone who wants to do something, some repair work in their plants, all of them has some standards are there, so everyone can use and connect. So all other industries are also able to manufacture with respect to that specification. So do you think that these standard the models that one industry uses, in future there's a possibility that standardization of these models is done? Like SIE system is one system that works all across different genres. So these models would have some parameters that are standardized, and then based upon the standard values, then future operators of the plant also make them as a benchmark and then work on.
Absolutely. So if you look at your control textbook, then across control, they will talk about instruments, and then they say 4 to 20 milliamps or 1 to 5 volts are the standards by which information or electricity, whatever is passed. But in practice, I think we have gone past that. If you buy a device today, you are going to say, is it foundation field bus compliant, right? And so that is a layer sitting on top of your 4 to 20 or 1 to 5, and it's passing higher level information, which can be used by the DCS or any other system directly. So the standardization of models, to me, the question the way you posed it. We are talking about, are the results exchangeable? We don't really care what is gone inside to generate the results. As long as the results are in a standard fashion, we should be able to exchange it across manufacturers, across devices and such. And I think that's very much not only doable but really desirable.
I can say that in the software, because most of these models come out through a software, so interaction between different softwares is not an issue anymore. So you have numerous platforms where something comes from, let's say, MathWorks software, something comes from Python. Some functions are from different softwares. They can all come together as part of a common platform. So those issues are resolved to a large extent.
Well, I wish my WhatsApp and SMS could talk to each other, but they don't. Right? So in that sense, it's not a technical difficulty, it's the willingness of the vendors to make them interoperable. And that's where the buyer decides, right? If the buyer says, I will buy your offering only if it complies to a standard, then they would force the producer or the manufacturer to give them that.
Hello sir. As Professor Sharad said that data-driven models can fail drastically in scenarios. So, can you share some practical scenario where you have seen that a data-driven model has failed drastically? And also, are there researches going on in making that failure, to soften that failure basically? Like he said that physics-based model do not fail drastically. The predictions might go here and there, but then they do not fail drastically. Are there researches going on where we can soften that failure?
Like for example, if you have a data-driven model, so it really depends on the data set on which the training was done. So if there is, if you are in that training space, you are, while using the model, you have gone outside that training space, then there was no training done for that point. So as a result, you might get a situation where the pressure, if I'll take the example of the Tennessee Eastman problem, which is very commonly used. So you might have where the pressure of the reactor, once you start going away from the space in which the training was performed, may give you an outlandish answer. So that is what I meant when I said that it can fail catastrophically. So on the other hand, you know that if it's a physics-based model, and even under assumptions of linearity, it might have some graceful failure where it slowly degrades as you probably go away. So one way out of this is what Professor Raj referred to as the physics-inspired neural networks. So in physics-inspired neural networks, you can take the first principles model, and the neural network basically becomes like a trial function. So if you're trying to solve a PDE and you use a trial function, it's a collocation method, then the physics-based neural network, whatever is the equation of that network, becomes a trial function. And now that trial, and so you can train it where you are trying to minimize the residual of the partial differential equation, for example. So here you see that the material and energy balances encapsulated in the transport model is also being honored by the machine. And you can augment it under a Bayesian setting, you can augment it using data. So you have data and you have prior knowledge which come together. So that is one way to go ahead.
Let me give you perhaps one more example that you probably are familiar with on how models can fail. I presume some of your labs here in IIT Bombay have biometric entry systems. Okay. Have you run into a situation where you put your thumbprint, you're registered, you're allowed to go in, but actually there's no one?
Yes.
Okay. So what is the model there? It's taking data from the sensor, usually it's an image sensor, compares it with the previous registered models, and then it says, is it close enough or not? So clearly, if you're registered but it's not allowing you to go in, it probably means that it has failed. Why is it failed? Maybe your thumb is wet, or you have oil, or the screen is smudged or whatever.
what does that lead to? The data that you have produced now is deviated a little bit. It's not like you lost your fingerprint, because then if you lost your fingerprint, you can't wipe it and put it again, it won't work, it should not work, right? So there's a small error which propagates to a nasty outcome. In this case, it just sets you back by another couple of seconds. So it's not a catastrophic failure, but imagine the same thing happening when you're talking about something more life-threatening or what have you.
So in the interest of time, we will take one last question.
Good afternoon. My question is regarding, like, as we are talking about AI and ML in chemical industry transition. So one individual who is working in research in academia, so what would be your suggestion toward acquiring skills? So in with the same transition as industry is moving.
Masters or the doctorate students are all available here, also the undergraduate students. So I would like to communicate that so whatever the technologies we are seeing, the AI, ML, digitalization, so it has various aspects into that. So first thing is like these technologies are useful only when you have a good chemical engineering knowledge. So that is the prerequisite, because this knowledge you are utilizing to develop these models. Then, like, if you are going to a particular industry, so you have to understand that process completely, from the data perspective, from the science perspective, operations perspective, everything. The control systems, existing control systems, what are the design parameters, right? So the basic understanding of the process, the expertise in the domain. So that is the base or foundation of these technologies. So when you merge this domain expertise with these technologies, then it becomes a robust architecture which can go to the plant. Otherwise, if the knowledge is not completely incorporated into that models development, then it may cause anything into the plant. So that is where, like, our challenges is we need to, like, give the confidence of the operators, the unit head, production head, and if they feel that we are not good in, for example, if I am working in carbon black process, and if I don't understand the carbon black process and I am developing the soft sensor control systems, so they will not allow me to enter into the premises of the plant. So that is the message I would like to give to the students. So be a good, get a good understanding into the chemical engineering basics, and the industry which uses the different the skill sets which you should acquire, must acquire, so that it becomes, you are like ready for the industry. So those are like the mathematical modeling, like whatever the equations you are, whatever the physics you are solving, you are capturing that physics into the mathematics, right? So you are solving those equations. So learn the programming languages, learn the software such as like MATLAB, wherein you can write a code, solve the equations, analyze the data, the MATLAB Simulink, wherein you can develop a control system, test various scenarios into that, how it can go into the plant. For the physics-driven modeling, you have like Aspen. So there are various commercial softwares which you have in the market, which you can use to develop the models for that. So you can develop the hybrid models also. So nowadays, like Aspen is incorporating the hybrid model. So it is a combination of physics as well as the data-driven model. So it becomes a robust architecture, right? Then coming to the equipment design and improvement of that process. So for that like the CFD analysis is done. So you can learn the CFD platforms also like ANSYS CFX, Fluent and all, right? So there are various skill sets which you can acquire during your studies, during your postgraduate and doctorate, so those you are ready for the industry, right? So chemical engineering knowledge plus this the technical skills. So as much as you can gather, you can acquire. So now you are ready for the industry and to develop all these algorithms which you can implement in the plant. And so the industries are looking for the people, chemical engineers who are good, who are having a good fundamental understanding of the chemical engineering fundamentals as well as the processes, the operations, having this technical skill sets. So it's a combination of all these things. And if you are there as a you have all these skills, then no one can stop you to take this digitalization to the new heights. So I hope I could inspire you guys, because when I started my career, I was started learning all this. Yeah. So I think people got bored through my lecture. So alarm is beeping. So yeah, I think I could answer or communicate or inspire you guys. Thank you.
I think it's been quite comprehensive. I would echo what he said, that AI is not exclusive single tool. It has to be among the toolbox, right? You need to know multivariate statistics, you need to know modeling, you need to know enough chemical engineering, because the domain is really where the key is. AI/ML has kind of got a lot of popularity, but actually the focus is less AI/ML and more on digitalization. I think that's the word that he very aptly used, and that's what one should be aware of. I think the only thing that students initially get surprised when they try to do when they start doing a real project is the data and the amount of cleaning that the data requires before. It's not like your homework assignment where you get a CSV file and it's all ready-made where you can change a new notebook. You probably spend 80% of the time in an AI project on cleaning the data. So be aware of it.
Sharad sir, any final comments?
So yeah, I would also echo that your credibility that you build is not by knowing how to run an AI/ML software. Your credibility that you will build will be based on understanding the domain that you're working in. For example, if why don't we ask our folks from CS or math department to solve the PDEs for us? Solving that PDE is just an extra step that I know, but it is really the ability for me to be able to write a model, which is my domain, and then I can extend that, my reach, by being able to solve it. In the same way, if I just know AI/ML and you work on a project, you'll be like a tech support guy. Okay, the guy who's solving the problem, the real value lies there. So now it is that, okay, you are solving that real problem. You've taken, let's say, a course on AI/ML where you understand what are these possibilities which are there. It's good to be aware of those possibilities and not be overawed by it. And when time comes, you can use them. You can deploy it as one of the things that you do.
Thank you, sir, for sharing your experience and knowledge. Let me hand over the session to our host, Niladri and Krishna.
We thank the panelists for this wonderful session. The discussion summarized the origin of data-driven chemical engineering and current state of the inroads of AI and ML into chemical engineering industry and some of the emerging issues thereof. It was also really fascinating for us to know that industries are also being run in an unmanned way. Now, we request Professor Sandeep Roy to present small tokens of appreciation to our esteemed panelists. Thank you, Professor Srinivasan. Thank you, Dr. Mankar. Thank you, Professor Bhartiya.